Hello and welcome to Empowered Learning. This particular lesson will be on how to use the Pythagorean and reciprocal identities to prove other identities. And so I have two examples that I want to do. The first one is now shown. We want to know, is the following equation an identity? Before we actually get started, what we want to make sure of is that we understand what an identity is. An identity is an equation where both sides of the equation are equivalent to one another for every x value possible to plug into them. And so for most of the trig functions, we have to follow the domain of the least restrictive one. So for every x value that we can plug into either side, it has to fulfill all those requirements in order to be an identity. So let's go ahead and work on this particular one. So we see that we have cosecant squared of x is equal to secant x divided by secant x minus cosine x. And we want to see if this is an identity. Normally when we work with these, we want to take the side that has the most quote unquote meat, and that would be the right side. So our strategy here is to take the right side and try to rewrite it to make it look like the left side. So for us to get started here, what we can do is we'll take secant x divided by secant x minus cosine x. And we know we need to get something with cosecant. So one good strategy to use would be to multiply this particular expression by 1, but make 1 look like the real number conjugate of the denominator. So that would be, in this case, secant x plus cosine of x divided by secant x plus cosine of x. Now we're doing that because we know in the denominator we have a situation where we have a minus b and a plus b. And we know we can get secant squared minus cosine squared. And that's important to us because we know that sort of mimics one of the identities that we can have here. So we're just going to do it and see where it goes. So let's go ahead and apply it. So here, if we do this in the numerator, we get secant squared x plus secant x cosine x. And in the denominator, we get secant squared x minus cosine squared x. Okay. And so now from this point, what we'll do is we'll rewrite everything that is in secant in terms of cosine. And so if you notice here, that this portion, we have secant times cosine. And we know that the secant is the reciprocal of cosine. So all of this would just end up reducing to 1. And just to make sure that I'm clear here, we know that secant is the same as 1 over cosine. And if we have it multiplied by cosine, we see here that that reduces to 1. So that's why all of this we're just saying is 1. So if we come here, we now have secant squared x plus 1 all over secant squared x minus cosine squared x. Okay? And so now from this point, we will write secant squared x as 1 over cosine squared x plus 1. And we will write the secant squared on the bottom as 1 over cosine squared x minus cosine squared x. Okay. So from this point, to sort of get us out of this jam and get rid of the fractions, we're going to multiply both the numerator and denominator by cosine squared x because that is the denominator of both fractions in our expression. So if we do that, we see here that in the numerator rather, if we multiply to both terms, cosine squared x times 1 over cosine squared x is just 1. And then we have a plus cosine squared x. In the denominator, we have similar sort of thing. So we will have 1 minus cosine squared x. Okay? Times, cosine, we have 1 minus cosine to the 4th. I'm sorry. And so now, from this point, we know that 1 minus cosine to the 4th x is the difference of two squares. In particular, we know that this can factor out to 1 minus cosine squared x times 1 plus cosine squared x. And of course, if we write our 1 plus cosine squared x in the numerator, we see here that we have a common factor that is reducing to 1. And so we still have our 1 minus cosine squared x here. And we know from our Pythagorean identity, namely that sine squared plus cosine squared equals 1. We know if we subtract both sides by cosine squared, we get sine squared. And so I'll show you that. So sine squared plus cosine squared equals 1. We subtract sine squared from both sides and we get this. So we know all of this is just equal to sine squared x. And of course, we know that 1 over sine squared x is the same as cosecant squared x. And so there is our answer. So we've proven that if we start off with secant x divided by secant x minus cosine x, we've eventually got to the point to where we now have secant squared x. So this is our first example. Now we will do the second example. Okay, so our second example is we want to show that 2 times natural log of absolute value of secant x plus tan x is the same as minus 2 times natural log of secant x minus tan x. So for this one, what we want to do is we can see that there is a secant x plus tan x and secant x minus tan x. The key to working this out is to deal with that particular expression and rewrite it in another way. So what we're going to do is, I'm going to show the Pythagorean identities right quick. And if you see here, we have one of the Pythagorean identities that has a tangent squared x and a secant squared x in it. And so that's important to us because if we can subtract tan squared x to both sides, we have the secant squared x minus tan squared x. And that's important to us because if we look back at what we're doing here, you'll see that we have the sign switch that we need. So what we're going to do here, our strategy is that we're going to start with the secant x plus tan x and rewrite it in another way. And one of the things that we're going to note before we get started is that secant squared x minus tan squared x is equal to 1. Okay. And again, that comes from the particular reciprocal identity that tangent squared x plus 1 is equal to secant squared x. So that's where we're getting that from. So we're taking note of that. We're going to say, therefore, secant x plus tan x could also be written as follows. we're going to take this and put it over 1, and we're going to multiply this by secant x minus tan x over secant x minus tan x. And again, the reason for that is we know that when we multiply the numerators, we have a plus b times a minus b, and that will give us a result of a squared minus b squared, or secant squared x minus tan squared x, where secant x is a and tan x is b. So for the numerator, we have secant squared x minus tangent squared x. And then in the denominator, we just have secant x minus tangent x. Okay. So, of course, we know that secant squared x minus tan squared x is equal to 1. So that would make this now just 1 over secant x minus tangent x. Okay. Now, if you notice, here we have the reciprocal of secant x minus tan x, which is sort of what we need here. But what we can do to sort of get it in the form that we need, we can write this as secant x minus tan x, all that raised to the minus 1. Now that's important because we know with logarithm properties, if we have, and I'll just put this to the side here, if we have log base a of something raised to a power, then we could rewrite it this way, where basically we're taking whatever the exponent is and pulling it out and multiplying it times it. Okay, so here we're going to now say the following. I'm going to say, therefore, we know that 2 natural log of secant x plus tan x here is going to be the same as 2 times natural log of absolute value of secant x minus tangent x, but all of that raised to the negative 1. And so, of course, we can now pull out the negative 1 out of the exponent per this logarithm rule here. So that gives us a negative 2 natural log of secant x minus tan x. And so this is exactly what it is that we were looking for. Because you see, in the beginning, we started off with 2 natural log secant x plus tan x, of course, absolute value of that, and we ended up with the same thing here, which we see down here. And so this concludes the video on proving identities using Pythagorean and reciprocal identities.